Hi, welcome back. So we're in Chapter 6, Prediction by RCC at the outline, Prediction by Classification in the subtitle of Introduction to the Concept of Classification. Just quick reminder, we are at this side of the map where we have previously accomplished the left-hand side of the map when the variable we are trying to predict to be continuous. Now we are talking about prediction of a variable where its possible outcome is a discrete kind of variable. This is the problem of classification. So what we're going to do now, we're going to establish the framework just like we have done earlier before when we have a regression problem. If we look at the range of xk, a form of a whole number, for example, could be any number of 0, 1, 2. These are not going to be considered as a number, but as a class. And the point is exactly the same as we had done before. If I would have all these variables of x1, x2, all the way to xm, I would like to consider them as an input to some kind of a function. And then we're going to spell out a value, for example, the y hat or my prediction. And this value will represent any of these classes that xk might take as in its range. This is the problem of classification. But the only things or the only challenge we could see quite clear that xk here, this variable, its possible outcome is a kind of discrete. We need to alter this f of x, which we were using it previously in the linear problem as, for example, alpha 0 plus alpha 1, x1 plus alpha 2, x2, etc., etc. The outcome of this guy is going to be a kind of a continuous value number. The y hat, what we are trying to predict here, it's a kind of a class, so it's not going to match the outcome of this function. We have to start to think from this. I'm going to establish the framework through 3 important steps, which is actually kind of govern the idea around prediction in principle. Maybe we have spoken about that in the introductory videos earlier on. So the first step, what we want to do is to establish our f of x, or a function that basically is taking a certain input, which is going to be, of course, the x vector of each value here. And then it's going to spell out this y hat, or the prediction that we're talking about. This is the first thing we need to establish. Actually, either the problem is regression or classification, this step is mandatory. We have done this f of x following this linear combination. And the second thing we need to do, well, we want this loose function that is going to investigate the actual label of the variable we are trying to predict and the prediction that f of x provided us with. Basically what we want the minimum value of this loose function of y and y hat. We are looking at a set of alphas that minimize this loose function, and this is where we need to look at the third step of this framework, which we call it the derivative, in terms of this vector of alphas that we're talking about. Sometimes you try, this derivative will lead you to a point and you think actually this is the best alpha that you can do, and you can do better than that. That's true because your capacity according to the value we have is not going to be helpful too much. That's why we've learned the technique of transforming the actual feature of this variable itself. For example, if I transfer this x1 to a polynomial or maybe radial basis function, sine function, cosine function, these transformation will help me actually to improve values that I'm assuming for the alpha, so to speak. This is the framework of classification. Actually, it is the same for any kind of a prediction as long as we are dealing with a supervised kind of problem. Let's now take this framework and apply it to the concept of classification. This presentation here, there is a kind of a separable line, and we know how to construct this line equation, and the outcome of this function, which is the f of x, right, is going to be kind of a continuous value. So but we are looking for only 1 or minus 1. This is what is the first altercation of this f of x have to take place. Now our first assumption that data set is separable. What I mean with data set is separable, let me draw to you some other data set. You might face a challenge now. There is no a specific line can be drawn in any ways. Maybe some other people say, well, it can be kind of a non-linear line. Well, you have just mentioned yourself. That means we can actually manipulate the fact by using our knowledge how to transfer this line to become a curved line. So let's first of all assume the simplest case when my data is really separable, linearly separable, like in this case. And then we're gonna from there establish the fact that we can actually take this model and improve it better if we reach out to case where we have a nonlinear separable situation, just like so. We have first of all to start to realize this equation, not from regression perspective, but from classification perspective. And to do that, I cannot do this with one feature just to show you what I mean. I'm going to actually include two features. I'm going to say this is x1 and this is x2 and this is my y. So basically I would have this point here and this point represent x1 value and x2 value. So if this happens to be labeled 1, we're going to make it a green. If it happens to be labeled -1, I'm going to change the color to red. When I have a classification problem, one dimension will be reduced, presented as a 3 - 1 that will be 2 dimension. It doesn't matter what is the color, red or green. Assume a point here. Like imagine there is a straight line that is passing through this point. You would have asked me, why did you choose exactly this point? Well, I hope now you are making the answer on your own. It is obvious that this point, it was the closest between the separation between these two classes. And this point is going to be my kind of a guidance. The first region, I will call it the red region, and the second region, call it the green region. But the point is that I'm going to look at this outcome of a function, f of x, and then I refer to my line here. And based on the outcome, I'm going to say, well, it is belong to this region or to this region. How to do that? But once again, and I'm saying, we don't want to think of this line as a regression line, a linear line, or so. You have really to start to change your understanding. I'm going to show you completely a different perspective that how you can start to visualize this line from different aspects. I am interested in a vector that is going to be perpendicular to this line. Let's assume alpha vector. So I'm going to draw this alpha vector. And don't forget, this alpha vector is going to have value of alpha 1 and alpha 2. If I take one data point, let's say I'm going to take this data point here, I could draw another vector from the origin to this data point. Now it is an x1 value and x2 value. Now if I ask you, what is the projection of x vector onto alpha vector? I mean, from mathematical perspective, we have come to understand, if I take the dot product between this vector alpha and this x vector, and I divide the value of the dot product by the length of this alpha, I will get a value that tells me how much this vector projecting on this alpha. This vector x here, it is obviously 2 by 1, and this alpha here, again, it is 2 by 1. I have to transpose this alpha in order to be able to do this multiplication right. So if I transpose alpha, this dimension become 1 by 2. It means the product is going to be only one value. And I divide that by the length of the alpha, and the length of the alpha again is scalar, so I will get only one value. And this value reference how much is actually projected on the alpha vector. Want to put all what I've said just now in one line. Okay, if I choose another point, let's say I'm going to choose this particular point. Projection of this vector on this vector is going to be 0. What I'm saying is that if I reach to some point on a line that projecting 0 on this alpha vector, it means this line is my classifier. So I would like actually to make some arrangement for this line. Let me alter this function in a different form. Now, when we looked at the projection of this line here, we get a value of, if you remember b, it was actually this value here. And this point was 0. And how about this point here? I have to extend alpha vector in the other direction here, and I will have this value here. Now, this value here is going to be minus b. So I will get this exact equation, exactly the same, but instead of getting a value of b, I will get a value of minus b. Then in the direction of alpha, by getting a positive value or completely the opposite direction, then we get minus b. If I have this case, then this altercation will be exactly like this. Alpha transpose x plus b in the length of alpha. So I hope you are following. I'm not doing something tricky here, just very clear. And we stick with this format. The actual value of taking any point on a line, and I'm asking you what is the projection then, it should be 0. We are looking at the equation of this line. So I could say, well, this is going to be alpha transpose x plus b by the length of the alpha is going to be 0. This is my classifier. Now, to make you much more familiar with the concept, I could say, well, this alpha transpose x again plus, instead of keep writing this b multiplied by the length of the alpha when I'm talking about this region here, I'm going to put just alpha naught, and that's going to be equal to 0. Or any other value that you are interested in. Is pretty much familiar to this, what we've been working about for a long time. According to classification problem, not a regression problem. So basically what we want to do in a nutshell now, maybe I could have chosen my alpha, the first values of alpha to be something, a vector like that, right? But this classifier here, it is obvious terrible one because I just classify everything above this line with one class, below this line with another class. How about if I shift this one some other direction? Well, this is way better than the previous one because here I'm classifying everything one class, everything else another class. I hope now I keep doing something until I reach to this a perfect separation where everything above this line belong to one class, everything below this line is going to be to the other class, and seems to be this is a very good line. Now what is the equation of this line? This is the equation of this line. We have just identified the f of x. So if the LC, the outcome of this, less than or equal to 0, consider this is a -1 class, for example. If the LC is larger than 0, I'm going to consider the class of 1. Now, how to choose these alpha? We need to define a loose function. So what is the best loose function I could think of it? If I take y minus my y hat, and the question is to you now, what are the possible values of y minus y hat? Well, let's think about it. Y here could be only 1 or -1 in this case. My prediction again could be 1 or -1. Well, the actual label is 1. I could have predicted 1. I could have predicted -1. Actual label is -1. I could have again predicted 1. I could have predicted -1. Make this subtraction of equation. It's going to be 0, 2, or -2. If the case happens, I got the outcome of this equation to be 0, it means I predicted correct. But the outcome happens to be 2 because of the sign positive. It tells me, well, you are predicting a negative as a label, whereby it should be a positive one. So you have to move in a positive direction. If the actual outcome of the error is a -2, it means go back to the negative direction. So how can we get to the best values of alphas knowing that our loose function is going to be like that? Well, we're going to take the derivative of this function. First in terms of the alpha 0, and then we're going to take the derivative in terms of alpha 1, and take the derivative in terms of alpha 2. So let's choose this point to be my ith observation, and this point to be my kth observation, and again I classify it wrong. Now I capture the error, my error value in the ith case here. Well, I'm classifying this to be positive, but it was negative, so it will be equal to -2. And my error term in terms of the kth, well, I'm saying this is negative, but actually it should have been positive. It's going to be 2. The rest is going to be 0. Well, I have an original value of alpha 1. Led me to this classification error. This is my original alpha 1. And I will add to it the justification of that error. So I will add this error, which is going to be some assigned directionality. I mean, just telling me which direction I should go. But this error must be multiplied by the derivative, which is we have just derived here by x1. Now this alpha 1 is making the updated rate. My error is 0. It means this entire term is 0. 0 multiplied by anything is 0. So it means my alpha, I am relying on the alpha 1 is good one. So don't change it. When I want to move this arrow to a different direction, either here or here, I don't want this to move too fast. So let's just shift a little bit of this, multiply this by something called learning rate. It's a small ratio, usually 0.1, 0.01, something small ratio to make the rotation under control. Now this entire term is going to be my update of the alpha 1. Same thing is going to be my update for alpha 2, just to change alpha 1 by alpha 2 and x1 by x2. Learning rate's the same, and whatever the error is. How about the alpha 0? Well, it's the same. Alpha 0 is going to be my original alpha 0 plus the error had occurred multiplied by the learning rate. Now, this is one approach of a linear classifier, which we call the perceptron. So to put all of this together, let's go ahead now and try to take all this theoretical presentation into a practical one with a real example using Python. Now, before we go on with Python implementation code for real data set, and I would like to show you the idea of the alpha vector that we've been discussing about. Imagine we would have this data set. Obviously, that we have like two classes, some of them at this side, some of them at that side. This data set, it's separable by a line. I'm going to look at the data set and I'm going to choose one of them. Let's just choose this point here, or observation of x1 and x2. Now, the first approach that I would like to do is to actually define a line, be a classifier, and this is the guidance going to be that is passing. And from this vector, actually, I can establish even a line. But the point is that we are looking for another vector to be perpendicular on this vector from A to F. This vector here, minus the 3 and 4, it is a perpendicular. You can justify that by yourself by taking the dot product between K and F, and you will see it is 0. What we have now, we have alpha value here represented by this K. Every point above this line is going to be belong to one class. Below this line is going to be to another class. Obviously, it's a very bad choice. So I have to move this line a little bit up in order to make correction, at least for this data point that I committed a mistake with. That's why in the derivative of x1, for example, we were multiplying the value of the feature of x1, or the value of x1, by the error, by the learning rate, and again added to the same value of alpha. And then I have to pick a vector that is perpendicular on this new line. So now I have a perpendicular vector. Now I am at the new classifier. This is my new classifier, and I am saying everything above this point belong to one class. Below this point or on the line, it is belong to another class. Obviously, this is a good classifier. So this is the visual presentation from vector aspect. I hope it's quite clear to you. Now let's go ahead and explore the session on Python and see how that works in real data set. So obviously, when I look at this data set, I'm quite a bit positive that perhaps there is a line that can separate the data. For example, I would like to show you an example. I know the actual value of the line because these are synthetic data. This is a possible classifier, right? But anyway, the idea is to find out, we should keep rotating this line until we reach to the lower value of errors. Now here I have two functions that I create. The first one I call predict, and the other one I call training the weights. After these two functions, decide on the learning rates, on the number of rounds, and finally I want to return what are the best weights. So here I just pass to this function called training weight. I pass the matrix, the learning rate, and number of rounds. Okay, so the training rates here, or training weights, first of all, it initializes a vector of W's. I'm gonna start looping inside my matrix at each row. I want you to send this row and this alphas to the predict function. Well, what predict function does is so simple and straightforward. To return 1 if this value of the activation value larger than or equal to 0. Otherwise, I want you to return -1. Now, basically, I'm going to start to calculate that. Update those W's according to the errors, as we said before. Once we do this, we could see in the first round we had 160, the error number, then went down to 124 and 100 and 0, then 0. So the last two rounds, we actually were able to pick up a good classifier. And these are the alphas that I have. So that was all about this linear classifier framework we've established. We want to take it one step further. For example, here is the first thing we could see: they are overlapped. Classifier of any kind of line is not gonna be a good one. Also, another case when you have like a data set where it is a separable. Yes, the line isn't gonna be exactly aligned. You're gonna maneuver this line to be a nonlinear, but it's still a separable data set, where you could say complete completely different when we're talking about this case of overlap data set. I mean, the classes are overlapped. Also, when there are multiple classes, not only two, as the case of binary we are discussing. This is where we're going to introduce a number of those algorithms that maybe can help us to figure out. So let's go ahead now and explore the case where we are going to pick up the logistic regression as our presentation for that. I will see you then.